All right, so we will continue on from Tuesday and start to talk about x86. So quick announcement, we now have the extension on A3. So please re-download the starter code. Both the extension and the extended extension is now extended. So you have. When is the deadline? Deadline is now, I think, 1, 2, 3. Let me check Canvas. I kind of forgot. I think 23rd for the original like extra credit deadline, and then 5 more days if I'm not wrong for the if you don't want extra credit, if you don't want to have more time on this, then 1 more day for the late token. All right. So the day on Canvas was inclusive of the late token already. Now we went through the code example here, right, to talk about the include main function that do A0, B5, add them together, return the result. And we show that these can be compiled and create the assembly code that looks like this. Now, today we'll go into the detail on what does move mean? What does add mean? How does x86 work? And to go there, right, we talk about register, which are really fast temp storage inside your CPU, where all the functional units in the CPU, like adder, multiplier, all the components that perform this task can access the register quickly within 1 cycle. These are also visible to programmers, and it computes the instructions directly on the access step. And a group of register is called a register file. It's just the name. It's like this is when I said register file, I refer to these are registers that you can use and program. So typically register is really fast compared to the memory, which is a lot slower. So when you buy the memory, when you want to access a piece of data, you are going to have to spend roughly 50 cycles or more to go and access your data. There's also a special register called the program counter. The program counter points to the current instruction. Why they are special? Because otherwise, without the program counter, you have no way to track where you are when you're running your code. So this allows your CPU to know that's the line you're running right now, and you're about to go to the next line. Typically, this is implemented every cycle, which means that I go to the next line. But occasionally, if I have if else or for loop, it means that I jump somewhere else. That's when the PC would be assigned with a different value. So the next thing is your fetch instruction, your command, right? You have the address for the command, which is the program counter, and you have the command itself that's stored in the instruction register. Instruction register store your instruction. Program counter store the location of your instruction. Now, the register in x86 has the name, as their name. It starts with ABCD, RAX, RBX, RCX, RDX are 8 bytes long register that you can use. So whenever I write %RAX, it means that I'm using the first guy. Now, from ABCD, it just changed to RSI, RDI, RSP, RBP. So this has to do with historical reason. In the 32-bit version of x86, we just have the first 8 number, and it was extended later. But before the extension was like you basically have to live with RAX, RBX, RCX, and RDX for the most part. And then there's a stack pointer and the base pointer RSP and RBP. Those two, we don't typically use it. And then there's RSI and RDI where you can use as well. Imagine you have a program using 6 temp variable, right? It can be quite painful. Now, modern x86 64-bit version, the designer say, hey, let's extend it. So have 8 more register from R8 to R15. At that point, they're like, I give up. I just do 8, 9, 10, 11 rather than ABCD because it makes more sense. So historical reason, we would use the RAX when you need to accumulate things. When we want to do sum equals sum plus x, sum will be in EAX or RAX. The base, these are used typically with the pointer value, for example, or the base of your array. These allow you to basically start from here and you can access a bunch of memory locations. RCX is used for the counter usually, and the RDX is used for temp data. Then you have the source and destination index, which, I mean, to be honest, nowadays is just another variable that you can use. All right. But when you compile your code, you will realize that RCX, for example, is often used when you have a counter. It just, yeah, it's been used like that before. So I have to modify the compiler. I'm not going to modify the old code because it works, right? So you see RCX associated with the counter, RBX associated with pointer more often than another, right? Oh, one more thing, which is the R in front suggests that I have the register and I take the whole 8 bytes. So when you call RAX, right, it's from byte 0 to byte 7, the whole 8 bytes. Let's say your program doesn't need 8 bytes, you just deal with the 4 bytes data like an integer. Let's say integer is only 4 bytes, right? One thing you can do to be more efficient, you don't have to bring the whole thing. You can use EAX to refer to the same data, but only take byte 0 to byte 3, byte 0, byte 1, byte 2, byte 3. So when you write in EAX, it's just the first 4 bytes of RAX. Then when you write AX, it's just byte 0 and byte 1, the first 2 bytes of RAX. And when you write in AL, it's just the first byte of RAX. Why do we need this? Efficiency. You don't have to move all these 32 bits data. You can just move 16 bits or 8 bits, right? So it applies for all the registers here. There's an R variant, there's an E variant, there's a nothing in front variant, and there's an L at the end variant. No question? Okay. So to move the data around, one of the most common instruction in x86 is the move instruction. And then as the name suggests, it's used to move the data from one place to another. Quick question, where can your data be? It can be in a register, it can be in the memory, right? The same instruction can be used to move the data from the memory to a register. It can be used from the move the register into the memory. It can be used to move from the register to another register. Same instruction. You just need to specify the source and the destination, and that's it. If you have the source, you have the destination, it works. Okay. The way it works is it starts with move with some suffix. We'll talk about suffix in a bit. Move Q will be the suffix that move forward, which is basically number of bytes into the destination. In this case, it's 8 bytes from source to destination. I move from source to destination. The overran that can go into the source can have 3 options. Sometimes I know the location of my data. For example, I know I want to move address 10 of my bad. I want to move number 10, the constant number 10 into my register or into the memory. I can put a constant number into the move instruction and we'll say move this value into here. So that's going to be the first option. We call this immediate. Whenever you go read assembly, if they refer to immediate, that's just a constant number. You can also use the register to specify that the register that holds the data I want to move. You can also use the parentheses that refer to the memory register, memory plus register. It means that I want to move at this location in memory to somewhere else. And we'll go to example, right? So we'll go to example in a bit. Okay. So here's the example. I can, for example, do move for 64-bit version of number 4 from source to the destination. After I run this, RAX will have the value 4. You see the source is a constant. So every time you want to refer to some constant, you put the $sign. The easier way to remember this, $sign specify the value, so we treat that number as an actual value. $sign in front of anything, that's the number I want as a constant. All right. So this means RAX takes 4. If you want to compare this to like what happened in C code, this is the same as almost I do temp equal 4. Right? The second variant, I want to move from a constant into a memory. It's not a register, into the memory. The way I would write this is the first part, sorry about this. The first part, as you can see, is the same. Someone tell me what's the difference about destination here. What is the difference between the first line and the second line? Yeah, the parentheses. Whenever you have, so kind of similar to the $sign. $sign means a value. Parentheses mean treat that as an address in memory. So whatever is in RAX, for example, let's say RAX is 1000. Treat that as the memory location address 1000. So here I move -20 into memory location 1000. In C, this is the same as I do store P equal -20 because P point to an address, right? You can also, the third one is, this is the simplest. I want to move from one register to another. It's like A equals B. The next one is fat finger, sorry. Register to the memory. It means that I want to move the value here into this address. Again, the only difference here is you have parentheses around it. Again, when you read assembly and you see parentheses, that's an address. Whenever you see parentheses, that's an address. Whenever you see $sign, that's a number. Whenever you see %, that's a register. If it's % inside the parentheses, treat whatever is in R10 in here as the address. So this is the same as I do store A equal B. I can also move from memory to a register by doing parentheses in the source. It means that go to that address, whatever data is there, take it, put it into R10. All right. And with this, we have the flexibility to initialize data to some constant like 0, 5, right, from the first version. We can also initialize an address to have a constant with the second version. We can do A equals B, right, in C. We can do pointer arithmetic with the fourth and the fifth variant, right? This allows you to basically now have basic way to assign data in C, but on assembly, all right? So that's why you see the move instruction everywhere. So you see the parentheses, right? There are different fancy version of the parentheses. We call this addressing mode. So parentheses around anything, that thing is an address. But here is, you can have the different variants of the parentheses. I will define the name first, followed by the example, all right? The example here, think of it as, I want to make it simpler, but here I can do absolute mode. Absolute means that I want to go to this particular address as an absolute value. I can do register indirect, means that I treat R1 as an address, I go there. I can do display space, which means I do R1 plus some number. Intel x86 processor does support these things. I mean, you can choose the processor to support one version, both version, or all three options. Now let's go with x86, right? So that's the next page. Each ISA will specify how to get the address. So you need to read the manual. Each ISA is different. That's why it's called addressing mode. And when you read it, it will tell you when you see parentheses, for example, how do you figure out the address? For x86, okay, first question, why do we need this? Let's say your address is in a 64-bit machine, which is all your computer right now, right? The number of bits that I need to represent an address without the addressing mode is going to be 64 bits. So I need the whole thing, right? And 64 bit is long. I mean, that's 8 bytes, which means that if I do any move instruction, I need at least 8 bytes. Really? That's long. I don't want that. So designers say, hey, let's have this fancy version to address it to different locations. So you can do some addition, some subtract, some addition, some multiplication on your address in a way that you don't need the entire 64 bits. Now you can represent an address using fewer bits, or you can treat the register value as an address. Now here's how x86 works. All right, this is the most important part, or not the most. The most important part is the move instruction. This is the next most is when you see parentheses, how does it work? There are potentially can be 4 things in there. The first thing in around the parentheses is the thing in front of the parentheses. The first item, which always will be there. The second item and the third item. So these are RBs need to have all the 3 things here are optional. If you don't specify this, by default, treat that as 0. In the case of S, treat it as 1. Now, here is your address. Down there is a little bit cryptic. So this is what I would do. Your address is going to equal, you start with RB, you multiply by, oh, my bad, sorry. Eraser. RB plus D plus RI multiplied by S. All right. D can be any constant number. RB and RI are registered. S is another constant. So the address is going to be RB plus D plus RI multiplied by S. Again, for example, yes. Oh, okay. So the point of having D and F is actually it's quite convenient when you think about how you program. For example, let's say you do this for int I equals 0, I is less than n, I plus plus, right? And you do a of I equals 0. Now, let's say a is an array of integer. How big is one integer? 4 bytes, right? It means that let's say a is at address 1000, right? A0 is at 1000. A1 is at what location? 1004, right? So you can put RB as 1000. And RI is going to equal to the variable I here, this guy. So it's initially it's 0, then 1, then 2. Then you put S as what? 4. So this way, you can write one assembly line that says move 0 into right here.
So it only has to get the base value of 1.
Yeah. So let's say this is in EBX, and let's say this is in ECX, right? The variable I is at ECX, the variable RB is at EBX. You can do this. Move $0 because you want to initialize to 0 into EBX, right? The base. ECX and 4. And you loop. You just write one line, the next line, loop. The first time you do this will be move 0 into 1000. The next time, move 0 into 1004, and so on and so forth, right? So this way, you can quickly go through without changing the base, without changing the RI, the index. The reason why we have the subscript I is the index into your array. Scale is how big is my data size? Is it 1 byte, 2 byte, 4 bytes, and 8 bytes? D, sometimes you don't want to start at 1000. Sometimes it actually can be like displacement of certain location. D is used more often when you have function call, and you'll see in a bit. You'll see it the next week basically how. In that case, you want to go like here -8, here -4. But yeah, great question. So hopefully that's more clear on why do we have this fancy thing.
It is more clear, but still, like, couldn't you just use RI? I know everything.
Yes, you can then not using this, but every time you would have RI add by 4, right? But
you can never change it.
The downside is with this only one move instruction, you can do 1000 plus I multiplied by 4 in one instruction. Otherwise, if you don't use it, if you just do assign 1004 to Ri and you keep incrementing Ri and you move to Ri, right? It means that the next line, what you have to do is to increment Ri by the counter multiplied by 4. So you need to do multiply, then an add in a separate instruction, so that takes more time. So that's why this is a little bit faster. And if you sum it up, let's say you have to implement this loop, right? It's actually not a little bit faster, it's quite faster because every iteration you save like 3 more instructions. The multiplication and 2 addition. So from 4 instructions, you finish everything in 1 instruction. So that's like 4x speed up. If you assume that everything takes the same amount of time. So now, before we do a quick break, I want you to think about how do I write this swap function in assembly, because there's a really, really easy way how to do this. And the swap function here, I want to swap the value of x and y. I pass in the address and make sure temp1 equal x, temp2 equal y, and then swap them together. You don't have to return because by the time you return, the 2 values is already swapped, right? So the assumption is before the function call happens, the value of x is in RDI, the value of y is in RSI, the value of temp1 is in RAX, and the value of temp2 is in RDX. Hint, use move kill. But the whole thing can be translated each to move kill instruction. All right, so let's do a 5 minutes break and we'll resume and answer this question. All right. Recording. Okay, so how we do this? All right. First line, what's the source and what's the destination?
Source, 2 parentheses, percent RDI.
Yes. And we put it in where? So you don't have to do parentheses because in this case, temp is a value. It's not. It's a register, right? You don't need to do pointer referencing in this case.
Yeah, I'm saying you have to end the parentheses.
Yeah, it's right there.
Oh.
Sorry, my handwriting is too bad as well. So here is percent RSI, right? You write it into RTX. Over here, temp2 becomes the source. So temp2 is RDX. You write it into the location of X. So that's percent RDI. And the last line is percent RAX. You write it into percent RSI. That's it. The reason why we show this example is because it has a really, really nice conversion into the move statement, right? As you can see, you can write assembly. My job is to make sure you understand this, but minimize assembly. All right, so that's one quick fix, right? Oh, that should be correct already. My bad. Move to, because we need the whole 8 bytes because our data is a long. Long is 8 bytes, so we do move kill and arm. If it's an integer, you just do move, so that's the 4 bytes version, and move address still has to be RDI and RSI, but the value is EAX and EDX is okay. Now, we show the move instruction, right? Now, let's say I don't want to move things. I just want to compute the address and store the address into some location. I want the destination to have my address. So in this case, the source is the addressing mode, the DRBRIS format. Basically, what I'm doing is I compute this address and put it into my destination. Basically, I compute the value of my address and put it at my destination. Usage is, for example, let's say I want to get an address of some variable and store it to my pointer, right? Let's say P is my pointer and I want to store the location of the ith element of A by doing ampersand AI. Ampersand AI becomes the source. P becomes the destination. In this case, P has my address. All right, so we're done with this part, the first usage. I want to compute the address. That's it. I can do something like this. Let's say I do int star P, right? And then P equal address of some variable like counter. In this case, it would do let's say counter is in ECX. Let's say counter is in ECX, right? What would happen is you can do LEA on ECX, right? This give me the address, right? Point to by ECX into, let's say P is at EAX. Let's say P is at EAX. It means that I want to get this address and store that in EAX, and that's all. So that's the primary use. The second use here is the trick, all right? Second use here is a trick. To be honest, if you're writing assembly code on your own, I'm not going to do it this way, but when you compile your code, you see the compiler do this trick quite often. This is where you have any computation of this form, x plus k multiplied by y. This requires two operations, multiply and add. Multiply is quite expensive. We don't want to do that all the time. Add is also, it is non-zero cost, right? Can we do this cheaply? The way you can do this is here as an x. Let's say I have to do x multiplied by 12. I want to do x multiplied by 12. And again, multiply is expensive. We want to avoid this. The way I can avoid this from the compiler point of view is, let's say x is in RDI. RDI is x, right? What I am doing is I want to get 12x. Okay, I want to get 12x. You actually then realize that 12x is actually 4 multiplied by 3x, right? So first thing, if I can compute 3x, I can shift everything by 2. I'll get 4 multiplied by 3x. So that's the first trick. Once I have 3x, I shift that number by 2 positions. That would give me 4 multiplied by 3x. Because shift left by 2 means I multiply by 2 to 2, which is multiplied by 4. So my next step is, how do I do 3x? I have x as an input, right? I have x as an input. 3x is essentially, again, 2x plus x, right? It's 2x plus x. So one thing I can do is, this can be RB, this can be RI, and what's my S? 2. So I can write this as RDI plus RDI multiplied by 2. With RDI is x. This will give me x plus 2x, which is 3x. So the first line in the LEAQ command, take x as an input, perform x plus 2x through my addressing mode. So from x, I got 3x in one instruction. And that's cheap. Basically, this is fast. I can quickly do this in the hardware. Then I do shift left by 2, which is also really fast. I can do this in the hardware, which means I can do multiply by 12 quickly. How much faster are you gonna get? Not a lot, but like maybe 10 to 20%, which is quite a bit. Let's say you buy a CPU and say that CPU is 20% faster, you love it, right? So this is actually a good optimization. Now we have move and MUIC. The rest that I show here, they're pretty simple. Because add, subtract, multiply, shift left, shift right, arithmetic, SAR, shift right, logical, basically SHR, then XOR, and or increment, decrement, negation, not. You can write the description to the right. This is one of the slides that I would allow you to print it on the final exam and take it with you. But I don't want you to memorize this. But it should be self-explanatory that add is adding to a number. Subtract is subtracting to a number. The shift thing you might forgot a little bit. SA, shift arithmetic. So you have left and right. Then XOR, and, or, the rest are pretty self-explanatory, right? And you have source and destination. Always, the first thing is always remember, you overwrite the result into the destination. That's a unique thing about x86. Other architecture like ARM doesn't do it this way. ARM, you have source 1, source 2, and destination. So you add source 1 and source 2 right into the destination. For x86, you have source 1, destination becomes the second source. You write it to yourself. So it's as if its source is x, destination is y. What you're doing is y equal y plus x. How many people are wondering why do we do it this way? Why don't we have source 1 and source 2? Make more sense, right? Well, I mean, it's just back in the day, instructions are shorter, so we have to pack more bits. And if you want two source, you need more bits to represent source 1 and source 2. So it's the design decision is, okay, let's combine source 2 and destination. A little bit more annoying when you program, obviously, yes.
When do you use not?
Not Q, at the end, right? Well, whenever you need the not operator, so there are like code optimization that are cheaper. Like the logical operation down there, everything is really fast. Imagine single gate. Like imagine like even faster than add and subtract. So those are operations that if you can convert, we love this. We love this thing. So there are optimization trick that instead of doing some arithmetic operation, you change to like this logical binary operator. So in the real sense, you're not gonna touch this. The entity that would work on this is things like compiler. Compiler will try to analyze and see if it can go with like not or something simpler. Right? Yeah, but that's a great question. It's like, why do we need this? It's there to make it complete, and we love it because it's fast. Okay, so now we talk about basic operator. The second thing is what we call the processor state. All right. How many of you use a debugger already? Like the Visual Studio Code, and you go like debug line by line. Anyone try that before? If you try it, you realize the first thing, right? Somehow this program gives you the ability to stop execution in the middle and then allow you to look at the value. Right? There are two things that are special about this. Debugging mode is you stop your program, which most of the time you don't do that, right? You keep them running. Then when you stop the program, you can also look at the value of each thing in the program. When you stop the program, let's say you can freeze time, the processor, the CPU has some state. For example, this variable has number 5, this variable has number 10 at the moment. Those are the processor state. So the programmer can see things like what's in the register, what's in the program counter. So you can debug your code, right? So processor state means that things that are visible to the programmer. What are these? Register value. Register, you can control that, you can program. Anything you can program in assembly, these are processor state. The location of the start, the RSP, the current instruction pointer, RIP, which is program counter. In Intel processor, they call it instruction pointer, the same thing, the program counter, point to the current line where we are running right now. Then there are things like the status of the last instruction. Let's say I add two number and it produces an overflow. The overflow flag over here, OF, will be 1. Let's say add two number and the two number result in a carry, the carry flag, CF, will become 1. If I say subtract two number A and B, and subtraction result in a 0, sorry, weird. Subtraction result in a 0, the 0 flag becomes 1. Let's say I add two number or do some operation, and I got a negative number as a result, sign flag will become 1. So CF is carry, as the previous operation result in a carry. 0 is has the previous operation result in a 0. Sign is negative. Overflow means literally my number overflow into the, like let's say I'm doing 32-bit plus 32-bit. Overflow means that I do something, result in a 33rd bit. Overflow into the size that I can contain. These allow things like if else and for loop. For example, if I do if A equals B, right? How do I check if A is equal B or not in assembly? One thing I can do A minus B. I can do A minus B followed by check what flag? 0 flag. If A minus B results in a 0 and there's no sign, there's no overflow, there's no carry, it means A equals B, right? So I can use this processor state to control my program. And because I said already, the CF, like CF, SATF, SF, and OF, these are condition code. Each one of them will be set to 1 when the condition becomes true, such as carry, 0, sign, and overflow. And most ISA on top of x86 will have these condition code as well. But you have to look at the detailed manual and they will explain when will this become 1. In x86, it's set to 1 whenever the last instruction results in whatever condition happened here. These are set implicitly, so whatever code you run, they'll get set automatically for every instruction except for one guy. Yes, LEAQ. Be honest, I think there are also many more instructions in x86 that might not set the condition code because x86 has so many instructions. Check the manual, but the one we will use so far will by default set the flag. Now, the next thing is now that you have the condition code, right, you can then do comparison. You can, for example, compare two numbers. You can compare two numbers. You can do CMPQ source 1 and source 2. It would set the carry if the most significant bit has carry out. So what it does is this compare will do source 1 minus source 2. You do the subtraction of the two numbers. If source 1 equals source 2, this means that 0 flag will be 1 because the minus results in 0. Then there's a sign and overflow. The reason why it's different is if I do subtract, what's the difference here between subtract and compare? Compare also do source 1 minus source 2. Subtract also do source 1 minus source 2. The difference is compare doesn't modify source 2. Subtract, whatever the subtraction result, I write into source 2. Don't forget you have the destination in the subtract. So for compare, I just check the value, and the way the processor check the value, just subtract it. Okay. Once you have the compare instruction, you can then use condition like if this is true, go to here. If this is false, go to here for if else and for loop. Another useful instruction that used similar to compare is the test instruction. So you can do test source 1 and source 2, but source 2, source 1. This is the same as computing source 1 and source 2. So instead of source 1 subtract source 2, this is source 1 and source 2. And then write the result to the destination, which is source 1 here. Write the result in source 1. So source destination again, right? So you add them and you write the result into source, the destination register. So how the other thing you can do is to now that you have the condition code, right? The condition code cannot be saved. What I mean is, let's say I have instruction 1, 2, and 3. That's my program. I run 1, then 2, then 3, right? When I finish 1, I have some condition code up. And then when I finish 2, my condition code would get changed based on the result of 2, right? So the carry flag, sign flag, all these things will get shifted all the time for every instruction you run. And by default, it will get overwrite whenever you finish the next instruction. So here's the problem. What if I want to save my condition? Let's say I want to run instruction 1, I want to save the flag. I finish instruction 1, and then I know that afterwards, I need to use this guy in instruction number 4. I need to use the status of instruction 1 in instruction number 4. What do you have to do here? You have to save them, right? Because once you finish 1, then you go to instruction 2. Instruction 2 would change my flag. Because it's going to be depending on the last instruction you finish. By the time you have instruction 4 running, the flag will be corresponding to instruction 3, but you need the one from instruction 1. Okay? Are you all with me so far? Okay. All right. So these flags, 0, sign, whatever, right? It gets set for every instruction you finish. Okay. So when you finish instruction 1, you have a flag. The CPU has a flag. Now, let's say you move on to instruction number 2. The flag, when instruction 2 finish, the flag will be for instruction 2. The same guy will now store the new value, the 0, sign, carry, and overflow, but for instruction 2. All right. Then you move on to instruction 3. Now the flag is for instruction 3. Let's say you move on to instruction 4, but your program at the time say, hey, I need the status of instruction 1. How do you get it? Because it's gone. It gets overwritten by instruction 2, then instruction 3, right? Are you with me so far?
Yeah, you go backwards.
You cannot go backward. What you can do is when you finish instruction 1, you can save it. So the set instruction do just that. So set followed by the conditions. You set the destination, which can be EAX, RAX, RBX, to store the condition that you want. For example, set E means that I want to set to 0, the 0 flag. So you can do set E, set not equal, E is equal, set not equal, set S, set S is sign, negative number. Sign, not sign, greater or equal, less or equal, above and below.
Like remembering like best.
Remembering what actually happened and check the condition. Like you look at the condition first, is that 0? I save it here. Yeah. So the set X, right? One other quick note is it only sets the lower byte. So that's one thing. Because let's say you do set with the destination, right? And let's say you look at RAX right now. RAX has 8 bytes. The set instruction only write the result here, just the lower byte, and leave the rest. Whatever value there, you leave it, you don't modify it. And here's the problem. If you use set and then you need to use the data afterward, that can be an accident in accidentally using the rest of the bits because you forgot to clear that to 0. Right? So a quick note on this is the set is usually paired with the move CBL. Move CBL means that I clear the rest of the bit to 0. So if you want to check if x is greater than y, if x is greater than y, you would then compare x and compare y, and you set the result into AL. This is a set the result of the comparison. Then you move CBL to like over here. So the set instruction just handle this part, right? Then the move CBL, make sure everything here is 0. Now you only have the result of the set. That's it. So most of the time when you have this, you're gonna do the two things, set and move CBL, set move CBL. That's why if you compile something and you need the condition and you look at the assembly, you see move CBL, you're like, what the heck is this? It's just to clear the rest of the bit. Yes.
How would you use the
Oh, here, right? So after you do the set instruction, the carry bit it can be then used with like things like like the branch instruction. Branch means that depending on the condition, I would jump here or I would go to the next line. So it's then used in condition with another set of like program, part of your program that has to do with like x greater than y, x less than y. So instruction pointer is the PC, the program counter, right? It alters the flow of instruction. This is used to implement if, else, or for loop. And it can be modified. It can be modified using control instruction, which are these guys. Jump is simple as the name suggests. I jump to that line. Okay? The way you remember jump instruction is jump. Depending on the condition, I jump to that line. So here, for example, JMP, I don't check the condition. I always go there. JE, jump if only the condition code earlier is equal. So there's JE, JNE, JS, JNS, JG, JGE, JL less than, JLE less than or equal, jump above, jump below. When next week when we roll around, we'll talk about for loop and if else in more detail. So you see the jump instruction in more detail. The gist of it is these are used to do if else for loop function call. In fact, I mean function call is actually called that it use a different command called the call, which call a function. Jump, think of it as a go-to command in C. If you never used it before, please keep not using it. Go-to is usually no one uses that. It actually make your code unsafe because you basically jump from one place to another without actual condition or anything. So it's kind of can easily break your code. But you can use this concept in assembly to implement a loop or if else. Now, we will end with conditional move. Conditional move is, let's say you have a simple if else instruction. Like if this is true, for example, if x is less than 10, y equal x. Something simple like this, all right? something simple like this. You can use the conditional move instruction because the first thing you realize is this can be done with move, right? This can be done with the move instruction, y equal x. Conditional move means that the if part will force whether you do y equal x or not. And we'll show you with the absolute example. So now, let's say I have the absolute different function, which the whole task is I want to compute the absolute of x minus y. So I want to return x minus y and the absolute of that, right? I want to return the absolute of x minus y. How do you implement this in C? I compare if x is greater than y, it means that I can do x minus y, and that's going to be a positive number because x is bigger than y. Otherwise, I'll return y minus x because y is bigger than x. Y minus x is going to be a positive number. That guarantees I will always returning a positive number. Okay. So here's this thing about assembly. If else generally means lower performance. It's kind of like something you learn as you go to like know how to build the hardware. You will then realize that if else can lower your performance. So one thing the compiler loves to do is get rid of if else. Get rid of if else because I'll use the next page. Sorry, I'm trying to find a free space here. Okay. Let's say you have a code that have if else, right? You have if else condition check at the end of the first block. If it's true, go to the left. If it's false, run the right part. The reason why it's loose, like it's actually not good for performance, is compiler optimization can become limited because you don't even know if you're going to the left or you're going to the right. If you can get rid of this if else and somehow make your program look like a big block, in this case, you can do more optimization. So that's the goal of the conditional move. So the way you can implement this and convert this if else here, right, into the big block here without the if else can be done here. So let's first assume x and y are in the RDI and RSI. Again, right? X and y are in the RDI or RSI. Now, I move x into RAX. I move x into RAX. Then what is RSI? Y, right? I subtract. This is y minus x. Now RAX has y minus x. Okay. RAX has y minus x. Because originally RAX has x. RSI is y, so you do y minus x and put the result into RAX. Okay, with me so far? Now the second step is RSI is y, right? So you do RDX has y. You then subtract x with y, so this guy RDX will have x minus y. This guy have x minus y. Then you compare x and y. Compare x and y. Then the conditional move is if x is less than y. If x is less than y. My bad. Actually, you compare y and x. You compare y and x. If y is less than x, if y is less than x, you want to return what? X minus y or y minus x? Y is less than x. X is bigger. You want to do x minus y. Where's x minus y? RDX. So I want to conditional move only if less or equal. Move only if y is less or equal to x. Move x minus y into the result RAX. So at the end of this line, RAX will have the absolute value. Okay. One thing you haven't learned so far, whenever you finish a function call, the return value is always assumed will have to be in RAX. So after that line, you're done. The function call is done. So we will actually learn next week. The return functions, when you want to return something, the return value is going to have to be in RAX. So in this case, you just have to figure out, are you putting y minus x or x minus y? And your condition in here is if y is less than x, you put x minus y into the return value. That's it. Now, with this conditional move, you don't have to do if else. There's no jump at all. You don't have to jump here or jump here. You make the whole thing a big block. In compiler, this block of straight line execution, we call this the basic block. It's like one of the units where compiler can do a lot of things inside to make it faster. So ideally, you want to make sure this block gets as big as possible. So this conditional move is used there. Okay. This is also sometimes if you keep reading, somehow you might heard of this technique called predicated execution. Same thing. Run this if certain thing happens. Otherwise, forget about this line. So why do we want to do this? Why do we want to do this? If else is expensive. What your CPU, so this is going to be outside of the content of this class a little bit, but now you might be wondering, why do I care? Okay, why do I care? Whenever you have an if else, your CPU actually always predict, are we doing an if or are we doing an else? Always do this. The issue is once you make a prediction, you keep going quickly. You actually do ahead of time. You actually keep doing the if part ahead of time. That's how your CPU gets really, really fast. The problem is you predict incorrectly. You have to flush the progress here, rerun. Flush and then rerun. Conditional move eliminate that prediction ever. You don't have to predict. It's like I just keep running. My status register, the zero carry flag, sign flag, overflow flag will always get set, right? So that I don't have to predict. Once I finish that instruction, it will be set. Then I can keep going. I don't need to predict. It guarantees I don't have to throw away work that I predict earlier. All right. Usually, conditional move is useful except if you want to use conditional move for a big if-else block, which means that you have to do two sides of the if-else. You don't want to do that. Basically, the first thing is, if you want to do, for example, val equal, and if p is true or not, if p is true, I want to do val equal store p, otherwise val is null. This play with pointer, and this can have weird side effects because you can have a valid pointer versus a null pointer. 0 is a null pointer, basically. So don't do this. Don't play conditional move with this is a legit reference, right? It's a legit pointer. This is a null reference. The behavior is different because if you try to dereference a null reference, the OS will kill you. That's all, and you eliminate process, right? So don't do that. Basically, the idea is both sides of the branch should not have any weird side effects. You're not gonna learn about what does it mean to have side effects until when we talk about functional language, which is a different class. So we will just wrap it that way, because I think it's probably the only time we talk about conditional move. There are things that you should not do with conditional move, but we do it. We talk about it here because this is when we talk about assembly, and I think this is like the only time in the semester and in your 4 years here that we talk about assembly, which is a good thing, by the way. That hey, if you want to go into compiler, now go back here and dig a little bit deeper. Otherwise, forget about it. Compiler will do this for you. All right. Now, Next week, we'll start talking about loops. In the meantime, we do have quite some time. We will talk about two things. Assignment trees, now that I see more questions. So I figured this is a good time to do Q&A for assignment three, as well as we have a new in class that has to do with arithmetic and logical operation. So play with that and see if we can compute the parity bits. So that's it for the lecture part today. I'll stop the recording now, and then we'll move on to Q&A. All right. Quick note about